everyone! In this video, we're going to go over orbitals. So if it's been a while since you've thought about orbitals, we'll try to review them as much as we can. So just to start, let's go back to our handout from last time. So we were going over VSEPR theory, and we talked about how electron pairs want to be as far apart as possible, which gives us these different geometries. And specifically, we talked about steric numbers, which are the number of lone pairs plus the number of bonded atoms around a central atom. Now, we're ignoring steric numbers 5 and 6 on this chart because those apply more to inorganic chemistry or transition metals, etc. So we're just focusing on steric numbers 2, 3, and 4. Okay, so just as a review, if we have a linear molecule with a steric number of 2, the central atom is sp hybridized. So that central atom there is sp hybridized. And then if we have central atoms with a steric number of 3, those are sp2 hybridized. And if we have central atoms with a steric number of 4, those are sp3 hybridized. Okay. Now, we're going to get into hybridized orbitals a little later in this video, but this is just something to keep in mind as we go forward. And one way that I remembered these different hybridized orbitals was if something has a steric number of 2, so it has 2 bonded atoms. We have an S and a P, so that's a total of 2 letters. And then if something has a steric number of 3, we have S and 2 P's, so that's a total of 3. And if something has a steric number of 4, we have S and 3 P's, which is a total of 4. So that's how I used to remember it. That way, on a test, I didn't necessarily have to go through the entire theory of hybridized orbitals. Okay, so let's go over some rules for filling in electron orbitals. So remember that electrons are located in energy levels or orbitals. We can draw an energy diagram here where we start with energy level 1, and that just has a 1s orbital. And then we go to energy level 2, which has a 2s orbital and 3 2p orbitals. And remember that s orbitals are lower in energy than p orbitals, which are lower in energy than d orbitals, which are lower in energy than f orbitals. So we could keep going. If you have a hard time remembering the order of orbitals, you can draw out or write out each orbital in each level. And we're just adding on orbitals as we go up in energy. And then you can draw arrows. So we start with 1s, then we go to 2s, and then that's followed by 2p and 3s. And then that's followed by 3p and then 4s, so things get a little out of order as we go higher up in energy. And then we have 3d and 4p. So hopefully some of this is coming back to you. Now, if we're filling out an energy diagram like the one I drew, also known as an orbital diagram, there are a few rules we have to follow. So the Aufbau principle tells us that electrons fill orbitals from the lowest energy to the highest energy. And then the Pauli exclusion principle tells us that each orbital can contain a maximum of 2 electrons with opposite spin. And then Hund's rule tells us that one electron is placed in each degenerate orbital first before being paired. So for instance, degenerate just means equal energy levels. So the two p orbitals in our energy diagram, those three orbitals have the same energy. So they are degenerate orbitals. So let's actually make a note here. Equal energy. And we'll go over some examples just to kind of refresh your memory. But first, let's look at what these orbitals, or what shape these orbitals have. So what shape does an s orbital have? So it looks like a sphere, right? So let's draw some three-dimensional coordinates here. So we've got x, y, and z. And an s orbital is really just telling us where an electron is likely to exist around a nucleus. So let me write that down below. So if our nucleus is in the center here, an s orbital electron, so let's say it's in a 1s orbital, it could exist here, here, here. If we ran this through a computer, it would show us something that's roughly spherical in shape. Now remember, it's hard to know the velocity and the position of an electron at the same time. So all we can do is guess the most likely location. So we end up with this sphere. Now what about p orbitals? What shape does a p orbital have? It kind of looks like a dumbbell, right? Or a figure 8. So I'm going to draw our axes again. Now remember, p orbitals, we have 3 of them. So if we have 3 coordinates, x, y, and z, the p orbitals are going to lie along different axes. So maybe this one is lying along the x-axis. The second p orbital might lie along the y-axis. And the last p orbital, let's say, lies along the z-axis. Okay. Now, in reality, these p orbitals don't sit separately from each other. They're actually all overlapping around the nucleus. So this would actually look like this, where they're all overlapping, but they're centered around the nucleus. Okay. So again, those p orbitals all have the same energy. So an electron, let's say we just have one electron in a p orbital, it has equal probability of existing in the px orbital, the py orbital, or the pz orbital. So we don't really know which one it's necessarily in at any given time. All right, now how many maximum electrons can exist in an s orbital? 2. What about the p orbitals? So let's just look at the px orbital by itself. How many electrons can exist in that specific orbital? 2. All right, so that's true for each of these. So then how many maximum electrons can exist in the p sublevel? 6. Okay. So now let's actually fill in some orbital diagrams or energy diagrams for these electrons, now that we've kind of reviewed some of the basics. So I'm just going to redraw that energy diagram from a couple of slides ago. And let's start with carbon. So if we're going to fill in this energy diagram, we first need to know how many electrons does carbon have. So you might want to look on your periodic table. So carbon has the atomic number 6, which means that it has 6 protons. And if it's a neutral atom, then that means it also has 6 electrons, because the positive charges have to balance out the negative charges and vice versa. Okay, so we have a total of 6 electrons for carbon. So now we're going to follow those rules we talked about on the first slide. So we have to start with the lowest energy orbital first. And remember, s orbitals can hold 2 electrons, so we're going to put 2 electrons in that orbital. And they have to have opposite spin, otherwise they're going to go flying apart, essentially. All right, and then we'll go up to the 2s orbital, do the same thing. So now we only have 2 electrons left. And remember, we're going to put 1 electron in each degenerate orbital first before we pair them up. And the way I kind of like to think about this is if you ever had to share your room before, at least I prefer to have my own room. So when I was growing up, I had to share with my sister, and I did not like it. I would have rather had my own room. And it's the same with electrons. So we're going to put 1 electron in each orbital first before we pair them up, but we ran out of electrons, so we only had 2. Okay, so this is the atomic orbital for carbon. And let's write the electron configuration for carbon. So if you want to try that on your own first and see if you remember how to do that, you can. Just pause the video. Okay, so with electron configurations, we're just listing out how many electrons are in each sublevel. So we'll start with 1s and write superscript 2 to indicate that there are 2 electrons there, followed by 2s, 2, and then 2p, 2. Okay, so now let's do the same thing for fluorine. And I would like you to try this on your own first. So if you want to pause the video and do that real quick, when you unpause, we'll go over it together. Okay, so how many total electrons does fluorine have? 9. Okay, so now we're just going to start from the bottom again. All right, so we've used up 4 electrons, and then we're going to jump up and put 1 electron in each orbital by itself first. Okay, so we've used 7 electrons, and now the last 2 electrons will have to pair up with the other electrons. Okay, so this is our fluorine atomic energy diagram. And let's write the electron configuration. So we've got 1s2, 2s2, 2p5. Okay, now if you're really feeling rusty on atomic orbitals and energy diagrams, I recommend going through the Skill Builder 1.6 exercise on page 15. I mean, I also recommend this for everyone in general, but specifically if you are feeling like, I don't remember this at all, that can help to give you some practice and hopefully jog your memory a little bit more. Okay, so now that leads us into molecular orbitals. So we just went through atomic orbitals and the orbital diagrams for single atoms. But what about energy diagrams and their orbitals for molecules? How do we draw those? So let's start with the simplest molecule, which is the hydrogen molecule. And remember, each hydrogen atom has one valence electron. Now, as those atoms get closer and closer together, we eventually will get a bond between them. So initially, when the hydrogen atoms were separated, they were unstable. But once they found each other and formed a covalent bond, they became stable. Okay, so now with molecular orbitals, we start with our individual atoms and their orbitals. So each hydrogen again has one electron. And which orbital is that electron in? A 1s orbital. Okay, so I'm going to draw one electron spin up and the other one spin down because we can probably guess they're going to come together and form a bond, so they have to be opposite spin. Okay, now there are a couple of possibilities here for bonding or pairing up of these electrons. So we have either a bonding orbital and we call this a sigma bond, or we have an anti-bonding orbital. And we label this sigma star. So bonding orbitals have lower energy than anti-bonding orbitals, so they are more stable. So which orbital do we expect those two electrons to end up in? The bonding orbital, right? Because it's more stable, it has lower energy. And then we've run out of electrons. We only had two, so none of those electrons will be in the anti-bonding orbital. Okay, so electrons would prefer to be in the bonding orbital because it's lower in energy. And remember that these bonding and anti-bonding molecular orbitals come from the fact that electrons exhibit wave-like behavior. So you might recall that electrons have wave-particle duality. So they can kind of exist as a wave and a particle at the same time. But if we think about the wave-like behavior of electrons, so let's say we have a wave for one electron, and then we have a wave for our second electron. And then let's say they join forces. They can either overlap constructively. So actually, let me make a little bit of room here. So they can either overlap constructively. So let's say it looks something like that. So then that would be constructive interference. And that would be a bonding situation. But these waves could also overlap destructively, and then we have nothing as a result. And this would be the anti-bonding situation. So that's just a little bit of review on electrons and their wave-like behavior and kind of where these molecular orbitals are coming from. Okay. So now we also have hybridized orbitals. And hybridized orbitals are a way to explain how atoms bond, because if we go back to our atomic orbitals and we specifically look at carbon, according to this atomic orbital diagram, there are only 2 unpaired electrons for carbon. But we know that carbon can make up to 4 bonds. So what's going on here? So this is where that atomic orbital theory really falls apart. And we have to account for that by hybridizing our orbitals. So we do need to also consider molecular orbitals here in a way, because we are going to see some bonding going on. So let's specifically look at carbon though, even though we're looking at methane here. So remember, we've said previously that carbon can make 4 bonds. And our Lewis dot symbol for carbon shows that it has 4 unpaired electrons. Now, scientists came up with this hybridized orbital theory in order to account for that. So let's look again at the unhybridized energy diagram for carbon. Okay, so we said that we had 2 unpaired electrons in the 2p orbitals, but we need 4. So what we're going to do is we're going to combine the 2p and 2s orbitals. And now we're going to have our 1s orbital still, so that stays the same. But the 2p and 2s orbitals are going to combine or hybridize to make 4 sp3 hybrid orbitals. And now those 4 electrons that are in the 2s and 2p orbitals will each have their own space, and they're all unpaired. So now this is a better explanation for why carbon can make 4 bonds. Okay. Now, those sp3 orbitals are going to have an energy somewhere between the 2s and the 2p orbitals. So I tried to show that here. That's kind of in between the 2s and the 2p. Okay. So let's just make a couple of notes to really hit home here what was going on. So there are only 2 unpaired electrons in our original atomic orbital diagram. And then we hybridized. It's like a magical power, hybridized. And now we have 4 unpaired electrons. Okay. So let's talk about what sp3 hybrid orbitals actually look like. So let's kind of visualize it. So again, remember we're combining a 2s orbital, which is spherical, with 3 p orbitals. And I'm just going to draw them all facing up for simplicity. Now, if we combine all 4 of those, we're going to end up with something that kind of looks like a p orbital, except it also has some s orbital characteristics. So this is our sp3 hybrid orbital. So 75% of this is going to have p orbital characteristics, and 25% it will have s orbital characteristics. Now the other thing is, if we were able to measure the length of a lobe on the p orbital, it would actually be longer than the length of the lobe on the sp3. So the, let's see, where should I write this? So the p orbital lobe is longer than the sp3 lobe. So my drawing isn't to scale, but just keep that in mind. Okay, so what's great is if we take all 4 sp3 hybrid orbitals and put them together, so really this is times 4, we end up with something, let's see if I can draw this, that looks kind of like this. It looks like a little octopus almost. So those are our sp3 hybrid orbitals that are all combined. So imagine that that's a carbon in the middle. Now, what's great is this is going to help us figure out how CH3 forms its bonds. So remember, hydrogen just has a 1s electron. So now if we pair those up with our sp3 electrons, we get our molecule. So each of these blue spheres is a hydrogen. And I'm going to draw little electrons here just to show what's going on. It's kind of hard to draw these, but now we have paired electrons. Okay, now each of these bonds are sigma bonding. So they're sigma bonds or single bonds. All right, so let's go back and just review. So originally with our unhybridized carbon orbitals, we had only 2 unpaired electrons. So we would have only been able to make 2 bonds with different hydrogens. But once we hybridized the s and the p orbitals from energy level 2, we ended up with our hybridized sp3 orbitals, and there were 4 of them. So we had 1, 2, 3, 4 that were combined to make 4 sp3 hybrid orbitals. And then we put each of those 4 electrons in their own orbital. So they were unpaired, and now we could make those bonds with each of the 4 hydrogens in methane. So then we looked at what the sp3 hybrid orbital looks like. So it kind of looks like a balloon. And if we have 4 of those, and put them all together, we end up with our figure down below. And remember, everything wants to be as far apart as possible, so the angle between those different orbitals is 109.5. So I do like to think of these like balloons, because if you had 4 balloons and you tried to tie them all together, they are going to try to be as far apart as possible. So you'll kind of get this octopus shape, I like to think of it, or a tetrahedron. Okay, so I think we'll stop there for this video because we did cover quite a bit of review material. But next time, we're going to talk about other hybridized orbitals. So we'll talk about sp2 and sp. I will see you then.